Alright, in chapter 9 we're going to look at a slightly different procedure, but let's just see where we've been to sort of have a big picture of all the different situations we have covered. So when we look at hypothesis testing, we are comparing our sample to a comparison distribution under the null hypothesis, and then see if the sample suggests that there's been a change in the populations, so that we can reject our null hypothesis in favor of the research hypothesis. And the different comparison distributions that we have had so far correspond to different situations. If I have a sample of just one score and my population is known to be normal with the mean and the variance known, then I have my basic hypothesis test. I could also have a sample that is greater than just one score. I know the population, then I would look at the distribution of means instead of the population and look at and calculate the variance of the distribution of the means. Now the mean is the same for both of those distributions, but the variance is not. Another situation was when I have my sample and I'm looking at a hypothesis test involving the sample mean, or the population means by way of the sample, but I don't know the standard deviation, the variance. I would then have to estimate the variance, as we've seen, and then because of that estimate, instead of knowing it exactly, I have a t-distribution, but still the distribution of means, like before. So we looked at a slightly more general situation. Then we looked at the t-test for dependent means, where I have the same group of individuals in my population, and I'm testing them before and after some sort of treatment, where I then look at the difference scores, and I'm looking at the distribution of the means of those difference scores. And I still have a t-distribution. It's essentially a new set of sample scores that I'm looking at and how they are distributed. The last one we've looked at up to this point is where I have the t-test for independent means, where I have two different groups of people, independent, or individuals, independent of each other, and I'm testing two different situations, seeing if the mean is different in some way. There I assumed that the variance was the same, and I estimated the variance of the difference between the two, looking at each population individually and then putting them together for the distribution of the differences. So there is a big difference between these two. Distribution of the means of the different scores, where I merged the two scores first and then looked at the distribution, and the distribution of the differences of the two means, where I looked at the individual distributions first and then at the end put them together in a single distribution. Those two things are not the same, but if you read them quickly you might think there's no difference. There is a big difference between those two. So what we want to look at next is essentially this last little bit, the second of the two here, independent groups, but more than two, three or more groups, and comparing if there is a difference in between them in terms of the mean of the populations. So the t-test is sufficient for two groups of independent scores, or two independent populations. Now what if I'm looking at more than two? That is where the analysis of variance method comes in. So my research hypothesis is that there is a difference in the means, and my null hypothesis is that there is no difference in the means. Whether you write it as an equation or whether you write it in words, totally fine, but you have to refer to the means of the populations. Now again, my strategy is the same, but I'm going to have to come up with a different way of looking at it. My basic strategy is the same. When I look at the null hypothesis being true, let's come up with a distribution of some kind and then see how our sample fits into that. So under the null hypothesis, where the null hypothesis is true, we're now going to look at estimating the variance and then look at how the sample suggests what the variance actually might look like. So if the null hypothesis is true, all the different groups are the same. All the different populations have the same mean. I can calculate or I can estimate the population variance, which is now all groups together. The population variance, I can estimate that in two different ways. But if the null hypothesis is true and they're all really the same big group, those two should point to the same variance. There's only one population variance. So the first method is what we call the within groups estimate, where I'm going to look at each group on its own and estimate the variance from the sample of each group in the same way we've done before. Sum of the squares divided by the degrees of freedom, which is n minus 1. Then I will average those out to get an estimate of the population variance, because every sample is going to tell me a little bit. So I'm going to look at what each one says and then average them out to get an estimate for the population as a whole. The other method, which should also point to the population variance, is what we call the between groups estimate. So each group is going to give me an average score, a mean score, a sample mean. I can look at those sample means and say, well, how do those means vary between themselves? The between groups estimate. So I'm going to look at the variation among or between the group means or the sample means. Well, the group means by way of their samples. The samples are all that I have. So I'm going to use the samples in two different calculations, but if the null hypothesis is true, then they should all point to the population variance, because all the three groups are really all the same, because all the means are the same under the null hypothesis. So where does the variation come from? Well, if the null hypothesis is true, then within the groups there is some variation. It's natural. Not everyone's the same. There is variation inside each group. And due to chance factors, there will be some variation. And the between groups estimate, because I'm looking at the means of those groups, they're still going to reflect the variation within. But if the research hypothesis is true, the within groups estimate is still just going to look at within each population the chance fluctuations, the random fluctuations that naturally occur. But if the research hypothesis is true and then there is a difference, a shift between the populations, their means are different in some way, then the between groups estimate is going to have a higher variance, because not only does it capture the variance within each group, but it also has this variance between the means, because the populations are different. So the between groups estimate is going to be much bigger than the within groups estimate if the research hypothesis is actually true. And this leads me to my analysis of variance approach. That if the null hypothesis is true, then these two ways of estimating the variance should pretty much be the same. They're not going to be exactly the same, they're estimates. but they'll be close to each other. The ratio between over within is going to be close to 1. But if the null hypothesis is not actually true, and there is a difference between the means, the between groups estimate is going to sort of move away from the within groups estimate because it has this extra between means variance added to it. And the ratio will be greater than 1. So what this test is going to involve is I am going to calculate the variance estimate in these two ways, which we'll see in a second. Look at the ratio and then see if it's greater than 1, how much greater is it? Is it still something that could happen fairly often? Doesn't really indicate that it's extreme and there is a significant difference in my population? Or is it greater than 1 significantly to the point where I could say, look, there is a difference between these that I can't ignore due to just random selection, that the between groups estimate is significantly bigger, and that has to be because the groups are actually significantly different. Now the distribution that comes from looking at this ratio can be derived mathematically as well, which we'll of course skip, and it's called an F distribution. That ratio is an F ratio. And the distribution looks like this. So if I were to have many samples of whatever size, like whatever the size involved is, if I have many samples from my populations and I look at those two variance calculations in the ratio, all possible ratios are distributed like this. So it's going to be less and less likely to get large ratios far away from 1. And again, I'm going to have a cutoff F value now that tells me how extreme is extreme enough so that I can say, nope, there is a significant difference here. I'm going to reject the null hypothesis. Some of these values are common, a ratio of 2 or 3. That is going to happen fairly often. These areas signify probabilities. But once I get out there towards 5, past 4 and 5, then it's not that likely anymore. So if everything was actually the same, my ratio is not going to be that big. If it's going to be that big, if I calculate it as that big, according to whatever cutoff out there somewhere, then there's evidence to suggest that, look, this wasn't going to just happen by chance. I'm justified in concluding that chances are that this bigger F ratio is because there is actually a difference in the populations. And I have evidence to suggest that the research hypothesis may be true. So now the question, of course, is how do we calculate the two variance estimates? Well, the within groups estimate, I feel, is not really anything too strange. And we will see examples eventually. I'm just going to go through this first, get a feel for what it involves, and then by way of example we'll see exactly how the calculations go. So the within groups population variance estimate. I'm going to look at each of my samples, representing, hopefully, each of the populations involved. And I'm going to calculate the sum of the squares divided by the degrees of freedom, which is the sample size minus 1. Now, to make this fairly simple, I'm going to assume that all the sample sizes are the same, since it'll make the calculation, the formula, easier to work with. I can have the sample sizes vary a little bit, but just to keep these formulas simple, to get the idea across, we look at the simplest situation where the sample sizes are all the same. Just get rid of this. So now How do we calculate this? I just want to hide the bottom here a little bit. So I'm going to calculate the variance estimate for each population, from each of the samples that I have, and now I have multiple populations, 3 or more. And I'm going to average them out by simply adding up the variances and dividing by how many groups there are. So I don't think this is really anything too strange. I'm looking at a familiar thing for each of my samples and then just averaging them out. Add them up, divide by how many there are, which I'll call the number of groups. The between groups variance estimate is going to seem a little less clear right now, but when you think about it the right way, it's actually very similar. What I'm going to do now is I'm going to shift my attention to the sample means as the scores that I have to work with. So I'm going to have a bunch of sample means, and I'm going to take the mean of that, which I'll call the grand mean. As if now these sample means are now my little set of sample values that I can work with. And I'm going to estimate the variance using those values. So it's the sum of the square deviations from their mean, which I'll call the grand mean, divided by the number of groups minus 1, because that's how many means I'll have. That minus 1 will give me an estimate for that variance. But that is a variance estimate for the population, not the population. That is a variance estimate for the distribution of means, because the values that I worked with were means of samples. Now in the past, we've gone from the population to the, let's say here, distribution of my population to the distribution of means. How did we do that? Well, we looked at the variance here. Let's say I have a sample size n. We looked at the sample and we estimated the variance using that. Then, because my sample size is greater than 1, I have to see how the mean sits in the distribution of means. So I went to what we call Sm squared, not S. The variance of the distribution of means, and that was simply the population variance estimate over the sample size. Now you can write this then as the standard deviation is simply the standard deviation of the population over root n, whichever one you prefer. Right now we're just focusing on the variance, so I don't want to get confused between the two. So this n that I divided by here was coming from the sample size. Now if I want to go the other direction, which I do in this case, the distribution of means is what I have an estimate for, because I'm looking at a collection of sample means and calculating the variance among them, using that as an estimate for the distribution's variance, but the distribution is now a distribution of means. So now I have to go the other direction to my population, because I'm trying to estimate the population variance, that the variance within is a population variance estimate. So I need both of them to refer to the population. So how do I go from this back here? Well, if I just shuffle these things around, the population variance estimate is going to be n times the variance of the mean. And that is where this comes from. So this is now going to be my population variance estimate by looking at the between groups estimate. So I take the variance of the means here and I multiply it by the sample size, my original sample size, which is, again, that's another reason why for now we're just looking at the sample sizes being the same, so that this formula just stays as simple as possible. So a little trick just to keep in mind, that when I look at the means and their mean, I'm estimating the variance of the distribution of means. I have to go back to a population variance estimate. Once I have those, I will calculate the F ratio, variance between over variance within. I prefer to write it like this, but that is another option there. I'll just write it like this. And then I want to see, okay, well, what do my samples suggest for this ratio? Is it extreme enough or not? All right, let me just see if there's anything else I want to say. And I'll then compare it to this distribution. So let's just backtrack here. Let me rewrite this ratio. So my F ratio is going to be the variance between over variance within. Now each of these guys has a degrees of freedom with it. So this one I'll call the degrees of freedom between, and that comes from this number of groups minus 1. So I'll say it like this, number of groups minus 1. This one, the degrees of freedom within, is going to be the, the degrees of freedom for each of the population, for each of the samples. So it's going to be the degrees of freedom for sample 1, degrees of freedom for sample 2, and so on, for however many I have to compare. First one to the last one, however many there may be. So I have a numerator and the denominator. So both of those I need to look up my F scores, my F cutoff value. I'll need both of those in the distribution. So when I look at something like page 678, I'll see something like this, where the distribution table now looks a little more complicated. There are now two different degrees of freedom that combine to give me a specific F distribution. So the table is a little more limited for practical use in a textbook. The denominator degrees of freedom can vary. The numerator degrees of freedom can vary. Once I have each one, like 2 and 12 for example, I have 3 common alpha values that I'll use to find the corresponding F cutoff value. So this is much better if we look at an example. So the criminal record study, let me jump to the hypothesis test setup first, and then we will go to the actual calculation. So what I do here is I'm looking at the similarities. See how many things are the same. The steps in the hypothesis test are all the same. It's just the calculations inside them that might be a little different. So in this example, we have 3 groups. We have, and each group is given different information about the defendant. Group 1 is told that the defendant has a criminal record. Group 2 that the defendant does not, or sorry. does not, that has a clean record. And population 3 is the group that's given no information about criminal record or clean record. They have no information. And the question is any group more likely to give a guilty rating, a guilty decision for the defendant? So if I look at a guilt rating, I can measure how guilty the people perceive the defendant. And I'm looking at these three populations. Are they different, which I'm hoping to conclude, or are they all exactly the same? Is the mean guilty scale, guilty rating the same for all three groups, meaning that the information doesn't actually matter? So now, because I have three groups of people, they're independent, they're different groups, you can't be told they have a criminal record, and they don't. They're independent. I'm shifting away from a t-test, which would have worked if I had two, but now I have more than two. So that's what puts me in the analysis of variance area. My characteristic, well, my comparison distribution has characteristics of an F distribution, and I need to specify the degrees of freedom. But now if I look at the actual detail that's being given here, here is the detail. Can I zoom in a touch more? Yeah, sort of. I have three groups. So obviously this is going to change to 3. And the degrees of freedom for each sample, well, I have 5, so it's going to be 5 minus 1, which is going to be 4, plus 4, plus 4. So the 2 degrees of freedom that I'll use in my table is 2 and 12. Now I have to go and decide on the cutoff value, but in order to do that, well, in order to do that, I have to go to my table. So let's just see. Let's just visualize this first, so I know it's 2 and 12. So let's visualize what the F distribution looks like. Erase this a little bit better. So in this case, all my hypothesis tests will be one tail. So this is an F distribution, degrees of freedom 2 and 12, we said. Now, if we're going to decide on a 5% significance level, let's go look in my table where I would look for that. So I'm looking at a 2 column on page 678 for the numerator degrees of freedom, and I'm looking for a 12 row for the degrees of freedom in the denominator, and an alpha of 0.05 puts me at 3.89. 3.89 for my cutoff F score. F cutoff 3.89. And now I have to calculate what the F ratio is from my sample, see how that compares. Do I reject or do I not reject? Okay, so here's my sample. The within groups variance estimate is easier. I'm now going to calculate the variance for estimate for population 1, population 2, population 3. Sum of the squares divided by 4, degrees of freedom 5 minus 1, and I will simply average them out to get a 5.33. So let's call this my observed F ratio. It is going to be something over 5.33. So that one I feel is the easier one to do, so why not do it first? Now, what do I do for the between groups variance estimate? Now I'm going to pretend it's a new sample, a different sample. What are the sample values? It's the means from each of my original samples. So I'm going to have 3 of them. A 4, an 8, and a 5 coming from 4, 8, 5. They're shuffled around a little bit for no apparent reason other than to confuse me. In any case, I have 3 sample scores, I think of it, to work with. They add up, divide by how many there are to give me an average. I'll call that the grand mean, because these are means. The means of the mean of the means. It's called the grand mean, 5.67. Then I look at the deviation from this 5.67, square it, sum of the squares divided by 1 less, which is going to be 2, and I get 4.34. Now you think, oh, 4.34 there? That's not going to be a very big ratio, because I'm not done. 4.34 is an estimate for the variance of the distribution of means. My F ratio involves population variance estimates. So I have to multiply that by the sample size, the original samples, which would be 5, to get 21.7. So a lot of little things here to keep track of. But you do this a few times, it's not that bad. So I calculate my F ratio as 4.07. See where that sits. Oh, it's a little bit to the right. I'll exaggerate it a little bit here. Let me review this, right? Let me put it over here. 4.07, that's F observed, FOBS. So my conclusion is that the evidence suggests that there is a difference between the populations, otherwise the ratio wouldn't be this big. How big is big enough? My cutoff tells me that. And I can say that's more extreme than the cutoff value, so I do reject the null hypothesis in favor of the research hypothesis that says that there is a difference between these groups somewhere. It doesn't really say where, it just says between the 3 groups there is a difference. Yes or no? That's all it says. Does the evidence suggest that there is a difference? Let's look at another example just to verify this. But before we do, let's just visualize this by way of the slide. So I have my 3 different populations that I'll assume to be normal. I get a sample from each one. And then I look at how the F score sits with all possible F ratio scores that I could get. It sits over there. That is not likely to happen unless there is some difference between the populations. Let me zoom out a touch. Next example, willingness to volunteer. So what this is we have 3 groups again, and people are asked to volunteer under different circumstances. They're asked when they're alone, they're asked when they're with their best friend, and they're asked when they're in a classroom. How do they respond? How willing are they to volunteer in those 3 situations? So again, these groups are independent, and I have more than 2 of them, so I'm in an ANOVA analysis of variance situation. Let's see what I have to work with. Here's my information. I have a sample of 6 per group, which would give me, in my F ratio, the degrees of freedom in the numerator is the number of groups minus 1. So again, it will be 3 minus 1. The degrees of freedom in my denominator, which is the within group. So this would be between groups estimate, and this would be within groups estimate. That will be 6 minus 1 is 5, 5, 5. So 5 plus 5 plus 5. So I have F distribution as my comparison distribution, degrees of freedom 2 and 15. Now if I again want a 5% significance level, I go and look. Now looking for a 2 and a 15. 2 and a 15 on page 679 will be 3.68. So I visualize what's happening here. It helps me a lot. There is my cutoff, let's say. Pretend that's a straight line. Whoops, that's not straight either. What do we say? 3.68 for F cutoff. F cutoff. Now let's go and see what my observed ratio is. Oops, down for the detail. Well, I have my sample values here. Calculate the variance for each one, same as we've done many times before. Average them out to get 2.53. So my observed F is going to be over 2.53. The between groups estimate is a little more difficult. And there I'm going to look at the means. So I have 3 means. See that as a sample. Take the mean of that, calculate the sum of the squares, and where is that? And estimate the variance is 2.34. However, that's an estimate for the distribution of means. So multiply that by the sample size to get 1404, which goes in here. And I get an F ratio observed 5.55 all the time. 5.55, that is F observed. And I compare it to the cutoff, and I can clearly see that that is extreme. The only way I'm going to be likely to get something like this is if there is a difference between the populations, and I can conclude to reject the null hypothesis in favor of the research hypothesis. The evidence supports the research hypothesis. Do I actually know what the truth is? No, I don't know for sure. It's just the evidence suggests that the research hypothesis is probably true. And I also don't know exactly which groups are the most different, which groups are causing this difference to reject the null hypothesis. I only know that there is a difference. Alright, so you can look at this slide. I'm not going to read through this. Hopefully you see the differences, but also the similarities between what we've done before and what we're doing now. We have a different comparison distribution, different calculations involved in getting it, but in getting the observed score and comparing it. But the basic layout and the structure behind the hypothesis test, that is the same. It's the same. Let's get rid of this. And there are just a couple of things to talk about. So now from my original ANOVA test, the hypothesis test may show that, yep, reject the null hypothesis, so there is a difference, but where is the difference? I I could have what's called planned contrasts, where I now plan to test two groups at a time. Or maybe I have a suspicion where the difference lies, and I'm only going to pick some pairs of the sample values and test them against each other, and I'm back in either t-test if I want to be, or the same thing, just to keep it consistent, but with just those two samples in question. To see, are they different significantly? Where is the difference? Which two have the difference? So my between groups estimate, I'm only going to use the means of the two groups that I'm focusing on, that I'm investigating a little bit more closely. And I estimate the variance of the distribution of means using those two. So I'll just have a little two sample of means. Different grand mean, different number of groups would be two. But I mean, I'm not restricted to that, but that's usually what we do. We just focus on two groups at a time. You could change it a little bit if you want to, but know that the between groups estimate then changes according to whichever groups I'm now focusing on. I ignore the rest. But when I look at, and then going from that to my between groups estimate, the sample size is still the same, so that's the same. Then within groups estimate, I'm still trying to get the best, under the null hypothesis, the best estimate for the overall variance for my population. So I'm still going to use the same as before. I'm still going to use all the groups, as much information as I can to do that. So the only thing that changes is the between groups estimate. Then I'll calculate my F ratio as always and get something slightly different corresponding to that pair of groups, samples. Compare that to what might be a different F cutoff because my degrees of freedom, especially the between, well, only the between, will change to potentially a 1 because I have two groups, minus 1 gives me 1. So if I do that very briefly here, for my criminal record study, I'm going to compare the group that gets the information that the defendant has a criminal record versus the no information group. I suspect that that's where the biggest difference is. So let's test those two groups against each other. So then I recalculate the between groups estimate using only those two groups, only two of the means. Get a new grand mean. The number of groups is 2 minus 1. And then I get a between groups estimate of 22.5. The within groups estimate is the same. F ratio of 4.22. Different cutoff of 4.75. And it turns out that that is not very significant. It's not extreme enough compared to my cutoff, so I do not project the null hypothesis. So those two groups, based on the samples, the evidence, are not the two that is creating a significant difference. So you could then say that I'm going to have to test the others as well. What if I have an idea of where it might be, but I might be wrong? I might have to test them all. You would be correct that that is a possibility. The problem then is, without going into too much detail, is that if I test all the pairs, then every time I run a test between pairs, I run the risk of a type 1 error. That's my significance level, alpha. And if I then do it again for a different pair, I have that risk again, and again, and again, and again. And it systematically blows up a little bit, grows, to overall, when I'm done with all my tests, my probability of making the wrong decision might be much bigger than my originally planned alpha. Because I now have so many tests, each time running the risk according to alpha. In order to avoid that risk or limit that increased type 1 error probability, we have the Bonferroni correction, which is going to be much simpler than you might think at first. All I'm going to do is I'm going to take my original significance level and divide it by the number of pairwise tests I'm going to do. For example, and I'm going to use that significance level, a much smaller alpha. So I'm not going to reject it as easily, but overall I'm not running the risk of a type 1 error as much. So for example, if I have 5 planned comparisons and overall was a 5% alpha, I would divide that by 5 to get an alpha 1% if I do it one pair at a time. 3 planned comparisons, I would divide by 3. 4 planned comparisons with an original alpha of 1%, divide by 4. Now when you look at this and think about it for a second, you might say, well, if I have a lot of these, I might not ever reject anything, because now my cutoff is so extreme that, yeah, overall I want to be safe and not make the wrong decision, but I'm never going to reject anything at this rate. It is just a first fairly basic way of avoiding the type 1 error blowing up, and if my type 1 error is too high, then I have no confidence in anything I'm saying. The alternative is Schiffe's test that takes a different approach, that says, now do everything the same. Do your pairwise comparison, but when you get your F ratio, divide it by the degrees of freedom. So your basic hypothesis test is going to follow the same route. You're going to have your cutoff according to the pairwise, which is going to change a little bit because of the between groups estimate changing. You have your cutoff here. You're not going to shift the cutoff by way of a Bonferroni correction. You're going to keep it there. But when you look at, so this is your cutoff, when you look at your observed score, let's say it's over here, your observed F ratio, instead of doing that and comparing it, making a decision, if I do it like this, my type 1 error is going to systematically increase over all the comparisons. I'm going to divide this by the degrees of freedom between, which is essentially going to decrease this and shift it somewhere to the left, which I'm then not going to reject it as easily with this adjustment or correction. Different approach to try and not have the type 1 error blow up on me. So if I look at the criminal record check, I follow the procedures before, and I get an F of 4.22. If I divide that by degrees of freedom between, I get a smaller F, and I'm not going to reject it when I compare it to my cutoff value. So I'm less likely to reject. I'm not going to reject it as easily, so I'm not going to make a type 1 error as much. Because I have many tests, if I leave it the same as the original setup, I'm going to have a higher and higher probability of making the wrong decision the more little planned contrast tests I perform. Just see here, there was one more thing I wanted to do. We are making some assumptions in the ANOVA approach that all the populations should be normally distributed or close to normal. And by way of SPSS, I have some tests to see if my assumption for following a normal distribution is correct or appropriate. And even if it's just slightly off, it's still okay, especially if I have larger and larger samples. Another assumption is that all the populations should have the same variance. And I'll just say here that to attest to see if we can assume, a test for assuming equal variance in SPSS, it's called Levene's test. Levene's test. So even though we're not going to look at the detail of that, just be aware that Levene's test is going to tell me whether my equal variance assumption is okay or not. So this is a much more complicated test, with the null hypothesis being the variances are the same, and SPSS will tell me the significance level that I have for this test, whether I can reject the null hypothesis or not. The last little bit is looking at the effect size. Now, of course, this is going to be very different than what we had before, and the effect size calculation is now this, which is just going to give me an indication. Again, there are different ways to calculate effect size. I just want to have a way of comparing the effect of the treatment or the difference in the power as well. This is one way where I'm looking for the proportion of the variance accounted for. This is also called the eta squared value, or the correlation ratio, and I calculate it using my between groups and within groups estimate. So for my criminal record study, I would calculate it as a 0.4. I can also look at it by way of my F ratio by dividing throughout by the within groups variance estimate. I'll get this. You can pick whichever one you want to work with. It's the same. And Cohen's conventions for what means small, medium, and large: 0.01, 0.06, and 0.14. So with a 0.4 there in my example, that is a large, very large effect size. Same as before, we have tables to help us get an estimate of the power of the study by way of the effect size and the number of groups, essentially. Depending on where the effect size is, small, medium, large, I have an estimate for the power of the study. It's a small table, so my numbers might not be in here. You just have a rough estimate of whether the power is high or not. Another table that we can use that I find sometimes, so this is just different groups, 3 groups, 4 groups, and the sample size that I assume to be equal for all of them. 3, 4, 5, those are the common ones. And I can also use this table, which looks at a different way to get an 80% power in a different effect size and number of groups situations. What would I need for the sample size to get an 80% power? So if I have a situation with 3 groups and a small effect size, and my sample size is 400, that's higher than the minimum requirement, so I know my power is above 80%. Can't say exactly. It's a limited table. One more thing to say is that, oh no, that's it. That is it. So even though when you use this table, you won't get these situations exactly, especially when you look at these tables. It's just there to give you a rough idea of what the power is of my study.